Start.
Good afternoon, everyone. So today we are presenting detailed review with the topic real-time autonomous navigation and mapping using molecular estimation and vision data. So our team members are Farid, Vaibhav, Ganesh, and myself, Rohit. So here are the contents of this presentation. And coming to the problem statement, as in the phase 1, we had explained the problem statement and how we are going to do it. In this phase 2, we will just give a brief overview of the problem statement. The existing problems for our solutions are expensive LiDAR. So for LiDAR are nearly costing nearly 5 lakhs to 10 lakhs. Even though if we get that, we need to get a complex setup for that. Also, there are calibration issues with software and hardware, and we also are very heavily dependent on hardware. So what are our solutions? So our solution for LiDAR is, our solution is we are using a smartphone camera and we are using MIDAS, which will be an alternate for LiDAR, expensive LiDAR, and we are using ESP82, which will act like a brain in the whole autonomous car. It will be having a real-time navigation plus with the grid mapping or occupancy mapping. Coming towards the objectives of this project. So what are we stating in this project? We are developing a real-time autonomous navigation system like a robot. So what will this do? It will perform a molecular depth estimation using LiDAR. So how will it will use a smartphone mounted camera in the car for live illusion. And what will it do? It will detect obstacles within the path and it will avoid collisions intelligently. So how does that car move automatically? It will be using ESP82 with Wi-Fi communication. And while it generates navigation decisions using depth-based analysis. It creates a simple real-time occupancy grid map. So in the grid map, it will be having where are the collisions, where are the obstacles. So it will achieve a low-cost autonomous mobility without LiDAR. So recap of this. In phase 1, we implemented MIDAS manual depth estimation. We generated real-time depth maps. We developed a basic obstacle detection logic. We tested it in the software environment. And in the phase 2, what we have integrated ESP82. We have added live video streaming using IT webcam. We have added occupancy grid mapping, and also we have optimized with the depth estimation pipeline using MIDAS smart function. And the next system design will be continued from a friend Rohit.
Thank you, Rohit. So coming to the architecture flow, basically, as Rohit said, we are using IP webcam. It is a pre-built app to collect the data or the frames. And next we are using the deep learning model using Python language itself. In Python language, in deep learning, we are using a model called MIDAS depth, which stands for molecular depth estimation. And that model detects the obstacles in the path, then makes the decision. Then the decision will be sent to the ESP82. Then motor will be driven. So I will be showing how does it work. Actually, we are having very latency, ma'am. Camera IP webcam is installed in my phone. It will be always sending the frames to my laptop, and ML model is built in my laptop. So this will be sharing the frames to my laptop, and my laptop where ML model will be running, and the output of the ML model will be given to this code. So this code just is used to take movements of the car to move forward, to move backward. I think due to latency it might not be that much accurate, but it is working fine. Network is very low now, so that's the issue. Model. Network
Video.
in this we can see the detection. This is a real monitor camera. So now the wall has been detected, the car has been rotated again. Now it will be detecting this chair and it will be rotating to the right. Use the real videos. The same pre-built. one. Now the wall will be coming here. It will be detecting the wall and it will be turning. Again, it will be detecting the wall. Again, it will be detecting the chair and it will be rotating. So it is basically detecting the obstacles and avoiding the obstacles. So as I showed the model, the IP webcam streams the photo frames. The Python and the Midas, which is stored in my laptop, will be doing the ML works, and the obstacle detection will be done in the ML deep learning model itself. So the decision making output will be coming in my laptop. That output will be sent to ESP through Wi-Fi, and that Wi-Fi makes the decision whether to turn right, turn left. So this is how the robot navigation is working. As I said, capture the frame, generate the depth map. As my friend explained, the model itself detects the how much depth is the obstacle in from the camera. So if the depth is more, then it detects okay, there is much more free space in front. If the depth is less, if the object is near, so the depth between the obstacle and the camera will be very less. So that is the main logic what we are using here. Based on that, the system design, the workflow of the system is working. So the technologies used here is Python for deep learning, OpenCV for camera works. The PyTorch is used for deep learning model. The NumPy is for handling mathematical calculations, and Midas model is the molecular depth model. So I think I have explained all the part in the explanation itself. Camera, the depth estimation model, the obstacle detection, and decision making. So this is the main logic how we are implementing. So next part will be explained by Ganesh.
Thank you, Vaibhav. Coming to the challenges and solutions, as we see how the model is going to work, there will be when a car moves, the model will detect like the depth, brightness, and the dark spots. If there are dark spots in the straight and the right corner, then it will take a left turn where the brightness is high. So it is a rule-based model in which it will see where the brightness is more. From that direction, it will turn. The car will turn. So the challenges are to get high processing delay during the estimation, because we are getting delay due to Wi-Fi and everything. So we are going to use a very lightweight model. There are so many. We have transform model also in this. We are using a very lightweight model which is used rule-based learning. Then comes the camera stream latency. Sometimes camera frames can be latenced. So we are going to use a reduced frame size. We are not going to make it a reduced one. Bada images but we are going to take small frames during which we are going to detect how much dark spots and bright spots are there. Then we are going to use like we have an unstable ESP82 communication. If Wi-Fi is not working properly, we can't take the turn and accident may happen. So we are going to solve that also using an automatic reconnection logic. So if the connection is lost, it has to connect fast. Then comes an incorrect obstacle training decision. Improved threshold based navigation logic. Here we are using, since this is rule based one, we are having threshold values. As I said, where the brightness spot, if the left side brightness spot is more than center and more than the right one, it is going to take the left turn. This is how it is going to work. Then comes a real time mapping complexity, which is done by SLAM, which is a mapping model in which it's going to, in a geographical area, it's going to map its own grid, from which it's going to take left or right turn. Then comes high computation load and delay in robot response. Everything. SLAM.
Simultaneous
localization. Since it how is going to work means
So it will analyze the spatial.
it's going to take a geographical area, for example, Davangere or here Bati road. That is the Bati road in which we have turn. So it's going to take and it's going to make its own grid. So for the vehicle grid, we are going to take a turn. Dark spots will be there and bright spot will be there. Where the bright spot is going to take a delay in robot response. So in the future scope, what we have, since in this model it is all rule-based one, the first thing we are going to use is reinforcement learning, in which we are going to make it autonomous. Since through feedback one, we are going to make the model learn on its own how to take decisions how to take certain decisions. We can't wait for our Python model or cloud-based model to respond in the meanwhile time. So then we are going to use sensor fusion. In sensor fusion, we are going to use two cameras instead of one camera. Stereo vision, in which we are going to use two different cameras, left and right camera, which is going to detect the images. Then monocular depth estimation is another one. We are going to calculate the distance and the estimation, depth estimation, image depth estimation, then actual distance estimate. We are going to combine those things, mapping. For example, value 200 bantu midas and distance is 20 centimeter or 20 meters. ಎರಡನ್ನು ಕಂಬೈನ್ ಮಾಡಿ ಮಾಡೆಲ್ನ ಟ್ರೈನ್ ಮಾಡಿ, ಸೊ ಇಟ್ ಕ್ಯಾನ್ ಟೇಕ್ ದ ಡಿಸಿಷನ್ ಹೌ ಟು ಟೇಕ್ ದ. ದೆನ್ ರಿಯನ್ಫೋರ್ಸ್ಮೆಂಟ್ ಲರ್ನಿಂಗ್ ಆಸ್ ಐ ಸೆಡ್. ದೆನ್ ultrasonic sensor ಇಂದ we are going to detect the distance ಎಷ್ಟಿದೆ ಅಂತ. Then IMU sensor ಅಂತ ಬರುತ್ತೆ. In IMU sensor it's like how much speed the vehicle is appearing in front of us, acceleration ಎಷ್ಟಿದೆ vehicle. Based on that we can take the sudden decisions to right or left. So these are the few future work which we are going to do. So next will be explain my friend Farid.
Seeing a camera as a friendly and obstacle process. It can be done.
ಈಗ ಲೇಟೆನ್ಸಿ ಇದೆ ಅಲ್ಲ ಮ್ಯಾಮ್, ಅದಕ್ಕೆ ಬೀಳುತ್ತೆ. ಯಾಕಂದ್ರೆ ಇಲ್ಲಿ ಬೇರೆ ರೋಡ್ ಕಾಣಲ್ಲ ಅಂದ್ರೆ ಆಟೋಮೆಟಿಕ್ ಸ್ಟಾಪ್ ಆಗುತ್ತೆ. ಯಾವ್ದಾದ್ರು ಲೇದರ್ ಆಗಲಿ ಈವನ್ ದಿಸ್ ಮಿರರ್ಸ್ ಆಗಲಿ, ದ ಮಾಡೆಲ್ಸ್ ಆರ್ ಟ್ರೈನ್ಡ್ ಆನ್ ದಟ್ ಡಿಟೆಕ್ಟ್ಸ್. ಇಫ್ ದೇರ್ ಆರ್ ಮಚ್ ಡಾರ್ಕ್ ಸ್ಪಾಟ್ಸ್ ಅದು ಮುಂದೆ ಹೋಗೋದೇ ಇಲ್ಲ, ಇಲ್ಲಾಂತೂ ಏನೂ ಇಲ್ಲ. ಬೇಸ್ಡ್ ಆನ್ RGB ಕಲರ್ಸ್, ಮ್ಯಾಮ್ ಇದು ಥರ್ಮಲ್ ಸೆನ್ಸರ್ ಇರುತ್ತಲ್ಲ, ಥರ್ಮಲ್ ಇಲ್ಲಿ ಅದೆಲ್ಲ ಆಬ್ಜೆಕ್ಟ್ ಥರನೇ ಡಿಟೆಕ್ಟ್ ಮಾಡುತ್ತೆ. ಪಾಪ್ ಇದ್ರೆ ಅಷ್ಟೇ ಜಸ್ಟ್ ಇಂಟರ್ನ್ ಇದೆ ಅಲ್ಲ, ಅದಕ್ಕೆ ಸೊ ಅದನ್ನೇ ಟ್ಯಾಕಲ್ ಮಾಡೋಕ್ಕೆ 2 ಕ್ಯಾಮ್ರಾಸ್ ಯೂಸ್ ಮಾಡಿ ಲೆಫ್ಟ್ ರೈಟ್. If we take all the advancement and it comes
ನಾವು ಇಲ್ಲಿ ಮಿಡೋಸ್ ಮಾಡೋದಿದೆ, ಅದು ಡೆಪ್ತ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡುತ್ತೆ. ಇಮೇಜ್ ಕಲಿತು ಆ ಇಮೇಜ್ ವಿಡಿಯೋ ಇರ್ತಲ್ಲ, ಆ ಒಂದು ಇಮೇಜ್ ಫ್ರೇಮ್ ಕಲಿತು ಆ ಇಮೇಜ್ ಡೆಪ್ತ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡೋದು. ಡೆಪ್ತ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಅಂದ್ರೆ ಈಗ ಇದು ಆಬ್ಜೆಕ್ಟ್ ಅಂದ್ರೆ ಇದು ರೈಟರ್ ರೀಜನ್ ತೋರಿಸ್ತಾರೆ. ಇಲ್ಲಿ ಈ ಕಡೆ ಸೈಡ್ ಓಪನ್ ರೀಜನ್ ಇದ್ರೆ ಅಲ್ಲಿ ಡಾರ್ಕ್. ನೆಕ್ಸ್ಟ್ ಓಪನ್ ಸಿ ವಿ ಯೂಸ್ ಫಾರ್ ರಿಯಲ್ ಟೈಮ್ ಕ್ಯಾಮ್ರಾ ಪ್ರೊಸೆಸಿಂಗ್. ರಿಯಲ್ ಟೈಮ್ ಅಂದ್ರೆ ಅಲ್ಲಿ ವಿಡಿಯೋ ಪ್ರೊಸೆಸಿಂಗ್ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ನೆಕ್ಸ್ಟ್ ಇದು ಪೈಚಾರ್ಟ್ ಮಾಡಲ್ ಇಂಟಿಗ್ರೇಷನ್. ಪೈಚಾರ್ಟ್ ಅಂದ್ರೆ ಇಯರ್ ಮಿಡೋಸ್ ಡೀಪ್ ಲರ್ನಿಂಗ್ ಮಾಡಲ್ನ ಇಂಟಿಗ್ರೇಟ್ ಮಾಡ್ತೀವಿ ಮಾಡಲ್. ಅದು ಡೆಪ್ತ್ ಎಸ್ಟಿಮೇಷನ್ ಮಾಡೋದ್ರಲ್ಲಿ ಹೆಲ್ಪ್ ಆಗುತ್ತೆ. ನೆಕ್ಸ್ಟ್ ಇದು ESP82 ಕಮ್ಯುನಿಕೇಷನ್. ಇದು ವೈಫೈಗೆ ಯೂಸ್ ಮಾಡ್ತೀವಿ ಕಮ್ಯುನಿಕೇಟ್ ಮಾಡೋಕ್ಕೆ. ಹಾರ್ಡ್ವೇರ್ ಟು ಸಾಫ್ಟ್ವೇರ್. ಇದನ್ನು ಸಾಫ್ಟ್ವೇರ್ ಅಂದರೆ ಸಾಫ್ಟ್ವೇರ್ ಟು ಹಾರ್ಡ್ವೇರ್ ಕಮ್ಯುನಿಕೇಟ್ ಮಾಡೋಕ್ಕೆ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ನೆಕ್ಸ್ಟ್ ಆಟೋನಮಸ್ ರೋಬೋಟಿಕ್ ಕಂಟ್ರೋಲ್. ಅದು ವರ್ಕ್ ಆಗುತ್ತಲ್ಲ, ಅದು ಆಟೋಮೆಟಿಕ್ ಡಿಸಿಷನ್ಸ್ ತಗೊಂತೀವಿ ಲೆಫ್ಟ್ ಟು ರೈಟ್. ನಮಗೆ ಡಿಸಿಷನ್ಸ್ ಬೇಕಂದ್ರೆ ನಾವು ಲೆಫ್ಟ್ ಟು ರೈಟ್ LR ಅಂತ ಕೊಡ್ತೀವಿ, ಅದು ಡಿಸಿಷನ್ ತಗೊಂಡು ವರ್ಕ್ ಆಗುತ್ತೆ. ನೆಕ್ಸ್ಟ್ ಇದು ಅಕ್ಯುಪೆನ್ಸಿ ಗ್ರಿಡ್ ಮ್ಯಾಪಿಂಗ್ ಅಂದ್ರೆ ಇಟ್ಸ್ ಕ್ರಿಯೇಟ್ ಎನ್ ನಾರ್ಮಲ್ ಮ್ಯಾಪಿಂಗ್ ವಿಚ್ ಅಂದ್ರೆ ಅಪ್ಡೇಟ್ ಆಬ್ಜೆಕ್ಟ್ಸ್ ರೂಟ್ ಅಪ್ಡೇಟ್ ಆಗ್ಕೊಂತ ಆಬ್ಜೆಕ್ಟ್ಸ್ ಅಪ್ಡೇಟ್ ಆಗೋ ನೋಡ್ತೀವಿ ಎಲ್ಲಿದೆ. ನೆಕ್ಸ್ಟ್ ಇದು ರಿಯಲ್ ಟೈಮ್ ಸಿಸ್ಟಮ್ ಆಪ್ಟಿಮೈಸೇಷನ್. here ನಾವು ಗಿಡಕ್ಕಿನ್ನ ಇದೆ ಸ್ಮಾಲ್ ಮಾಡ್ಯುಲಸ್ ಮಾಡೆಲ್ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ಮತ್ತು ನಾವು ಇಮೇಜ್ ಫ್ರೇಮ್ ಇದು ಕಮ್ಮಿ ಮಾಡೋದು ಸೈಜ್, ಆ ಪ್ರೊಸೆಸಿಂಗ್ ಸ್ಪೀಡ್ ಆಗುತ್ತೆ ಕಂಪ್ರೆಸ್ ಮಾಡಿ. ನೆಕ್ಸ್ಟ್ ಇಸ್ ಕನ್ಕ್ಲೂಷನ್. implementing a real-time molecular depth estimation using other projects and developed autonomous obstacle detection and navigation, automatic obstacle detection and automatic decisions. Next is integrating smartphone based on live video as phone connect. Next is established ESP82 based on robotic communication. ಇದು ಸಾಫ್ಟ್ವೇರ್ಗೆ ಹಾರ್ಡ್ವೇರ್ಗೆ ಕಮ್ಯುನಿಕೇಟ್ ಮಾಡಿ. Achieving autonomous robotic movement using depth analysis. Depth analysis ಮಾಡಿ ಇದು ಲೆಫ್ಟ್ ರೈಟ್ ಅಂದ್ರೆ ಇಲ್ಲಿ ಇಮೇಜ್ 4 ಪಾರ್ಟ್ಸ್ ಡಿವೈಡ್ ಆಗುತ್ತೆ. ಸೆಂಟರ್, ಲೆಫ್ಟ್, ರೈಟ್. ಅದು ಡಿಸಿಷನ್ ಅದು ಅನಲೈಸ್ ಮಾಡಿ ಇಮೇಜ್ನ ಡಿಸಿಷನ್ ತಗೊಳ್ಳಿ. ಇಂಪ್ಲಿಮೆಂಟಿಂಗ್ ಬೇಸಿಕ್ ಗ್ರಿಡ್ ಮ್ಯಾಪಿಂಗ್. ಆಪ್ಟಿಮೈಸ್ ಸಿಸ್ಟಮ್ ಫಾರ್ ರಿಯಲ್ ಟೈಮ್ ಪರ್ಫಾರ್ಮೆನ್ಸ್. ರಿಯಲ್ ಟೈಮ್ ಪರ್ಫಾರ್ಮೆನ್ಸ್ ಮಾಡೋಕ್ಕೆ ಆಪ್ಟಿಮೈಸ್ ಮಾಡಿದ್ದೀವಿ. ಅಂದ್ರೆ ಇದು ಮಿಡಾಸ್ ಮಾಡೋದು successfully demonstrated on low-cost automated navigation project. Instead of high-cost automation, we use low-cost middle and single camera is made. currently project is completing certainly 70 to 80%. Currently 80%. Our future implementation when I said
Basically, gap is maintained. Only depend on model. Really, distance.